Okay, so next let's talk about the thermodynamics of an electrochemical cell. So, of course, if we're going to talk about thermodynamics, we have to talk about the first and second laws. So the first law tells us that du is equal to dq plus dw, right? Where we recall that dw is defined as the work done on the system, right? And so we can relate delta U, right, to the heat released and the work done on the system. And then we can break down the work into various components. So we can say that that's the work due to expansion against pressure, the work done due to moving electrons around, so the electrical work, and other possible terms. But those are the ones we're going to concern ourselves with. So how do we talk about this electrical work? Well, the incremental electrical work, dWEL, should be equal to minus the voltage times the amount of charge, so let's use d little q, that's moved. So this is the voltage, and this is the charge, right? So if we move charge across a voltage, that requires us to do work, and we could write that as minus v times the current times dt, since the current is the charge per unit time. So this gives us a way to relate our thermodynamic quantities to typical electrical measurements, right? So, so here now we can write our du. We're going to expand this out to be du is equal to dq plus dw due to expansion plus dw electrical, where this dw expansion is minus pdv, right? Okay, so that's our typical expressions, various expressions of the first law. So let's think about the second law. So the second law, we know, is basically just that the total entropy of the universe has to be greater than or equal to 0, but that allowed us to derive, and I'm not going to go through, of course, the whole derivation since that was the purpose of the class, that the free energy is equal to the enthalpy minus T times the entropy, and that we could write the differential of the free energy, the Gibbs free energy, at constant T, here let's specify it at constant T, as being equal to, oh well, no, let's just do total incremental free energy would be dH minus TdS minus SDT. So at constant T, dG would be equal to dH minus TdS. Okay. And then we could further look into the details of the enthalpy, right? We know that H by definition is U plus PV, and dH therefore is du plus PdV plus VdP, right? And we can further break out the energy to be dq plus d work of expansion plus dw electrical from the first law plus pdv plus vdp. But of course, this part is minus pdv. So what we get is that dH is equal to, this is for a reversible process. So dH for a reversible process would be TdS plus the electrical work plus VdP. And now we can write our dG, which we have in terms of dH and TdS, as dH minus T ds. So that just gives us d electrical work. And here this is reversible, right? We specified to reversible plus v dp. So at constant, so if we further specify that we're at constant temperature and pressure, which is typically the case, then we simply have a relationship that the electrical work is equal to the change in the Gibbs free energy, right? The reversible electrical work. So we can further relate that the work done, since work done by the system equals minus work done on the system, we have, the work done by the system is minus delta G. So the work done by the cell is minus delta G in the cell. Okay, so the maximum work that we could do at a constant temperature and pressure is just given by whatever decrease in Gibbs free energy we have. And we can relate this back again to the current. So let's note that just by our Kirchhoff's laws, right, I is equal to delta V, change in voltage of the cell, over the resistance, right? And we can further write that as the charge, the current is, by definition, the charge per unit time. And we can write the charge as the number of moles of charge times F, where F is defined as a farad. That's equal to Avogadro's number times the charge of an electron. Okay. So rewriting this, we have that the time for the process is equal to the number of moles times a farad times the resistance over the change in voltage of the cell. So that's just a recasting of those terms. And we know that the electrical work should be equal to the power I squared R times the time. So that gives us change in voltage of the cell over R squared times R times the time, which we got up here, N times a farad times R over delta V of the cell. So we get that the work done by the cell is equal to the number of moles of electrons that we've moved around times a farad times the change in voltage of the cell. Okay. Which should, of course, be equal to minus delta G by this expression up here. So the consequence is that the maximum work done depends on the number of moles moved and delta V, and is related directly to the change in the Gibbs free energy in the cell. Okay. Such that delta G is, right, minus N times a farad times delta V in the cell. And furthermore, we can see that the reaction will be spontaneous as long as we can lower the Gibbs free energy. So this will be spontaneous if delta G is less than 0. And there'll be work done by the system as long as the voltage of the cathode is less than the voltage of the anode.